Think about the following question. What is the radius of the largest k-dimensional ball inside an n-dimensional unit hypercube? Here, of course, k is less than or equal to n. This problem is a generalization to a problem in the Putnam mathematical computation in 2008. In that problem, n is equal to 4 and k is equal to 2. And we are going to try to solve this question in its full generality. The solution to this problem, to this generalized problem, involves lots of techniques in Euclidean geometry and linear algebra. So let's start solving this. First, let's look at some examples when n is relatively small. First, if n is equal to 2, k equal to 1, then we can easily draw a picture. In this case, our two-dimensional unit hypercube is just the square with side length equal to 1. And the largest one-dimensional ball inside this two-dimensional square with side length 1 is this full diagonal line segment, whose length is equal to square root of 2. So in this case, the radius will be equal to half of square root of 2. So in this case, the answer is half of root of 2. Now what happens if n equal to 3? If n equal to 3, k equal to 1, the situation becomes finding the largest line segment, because in this case, when k is equal to 1, one-dimensional ball is just a one-dimensional line segment. What is the largest one-dimensional line segment that can be contained in this cube? What is the radius of it? It's easy for you to see that this line segment is the diagonal line segment connecting two vertices of this unit cube with longest distance. Since the side length of this unit cube is equal to 1, this diagonal line segment has length equal to square root of 3. So in this case, our maximum radius will be half of square root of 3. Now here comes a harder question. What happens if n equals to 3, the k is equal to 2? Now you want to find the radius of the largest two-dimensional ball inside a three-dimensional hyper unit cube. Two-dimensional ball is a disk. So we want to find the disk, two-dimensional disk inside this three-dimensional unit hypercube. And in this case, you have to think a bit harder. And it turns out, in this case, the largest two-dimensional disk inside this three-dimensional hyper unit cube is this red disk inscribed inside this hexagon in green. And each vertex of this hexagon is a midpoint of some edge of this hypercube. It turns out this is the largest two-dimensional disk that can be put inside this hypercube. And now what is the radius of this? To find the radius, we first find the diameter for this two-dimensional disk. This diameter can be computed through the Pythagorean theorem. In this case, diameter will be the square root of 1 squared plus square root of 2 divided by 2 squared. This is square root of 3 over 2. So in this case, our max will be equal to half of square root of 3 over 2. This is the Rmax. And now, based on what we have obtained here, we can make a conjecture. The conjecture is that for general k and n, with k less than or equal to n, we have this Rmax equal to half of square root of n over k. Next, we're going to show that this guy is indeed the radius of the largest k-dimensional ball inside an n-dimensional hypercube. To make this problem slightly easier to solve, we can do the following simple simplification. Scaling up by a factor of 2. We may work on the equivalent problem of proving that the maximum radius of a k-dimensional ball contains a hypercube the n-fold Cartesian product of the closed interval from -1 to 1. So basically, what we are doing is that we translate an arbitrary hypercube to the origin and scale it by a factor of 2. Is square root of n divided by k. So this problem is apparently equivalent to the original one. The good thing about this simplification is that now this hypercube is symmetric about the origin, which allows us to use lots of techniques from linear algebra.